First, we'd like to thank everyone from M3 for giving us this opportunity. M3 as a whole has been a very memorable experience. We've all had a ton of fun. So without much further ado, here's the solution paper for Team 13429. In problem 1, we were tasked with calculating the percentage of semis that would be electric in 5, 10, and 20 years, assuming that the infrastructure for transitioning to electric trucking was already in place. And we began by comparing diesel and electric trucks, and we found that over the course of each truck's lifetime, the electric truck was around $200,000 cheaper, meaning that companies who wanted to maximize their profit would always purchase the electric semi. And the implication of this was that the production of electric semis was the limiting factor here. And so to produce our production model, we looked at the production of the Tesla Model 3. We felt the Model 3 was the most appropriate because when Tesla was working on it, it already had infrastructure for producing electric cars in place, just like a lot of these companies already have infrastructure in place for producing the electric semi. So we took the quarterly production of the Model 3, performed logistic regression, and came up with what we call a baseline function for our model. Now this baseline function is for the Model 3, and we want to predict the production of electric semis. So to get there, we rely on two of Elon Musk's predictions. The first is that Tesla's production of their electric semi will reach a steady state of 100,000 semis per year, and that it will reach this in 2024. So now we took our baseline curve and dilated it to fit these predictions. Our first dilation took place along the y-axis and reduced the steady state to 25,000 per quarter. So you can see here the numerator of our logistic graph, which is the limit, is now 25,000. The second dilation took place along the x-axis, and it allowed the steady state to be reached in 16 quarters instead of 9. And mathematically, the substitution took q to 9/16 q. And you can see here that the curve now reaches steady state in the 16th quarter. Now, this is just Tesla's estimated production, and we want the production for the entire industry. So in order to get this, we took Tesla's market share of electric vehicles, which is 53.79%, and we assumed it'd be the same for electric semis. And by doing so, we were able to calculate the total production. Now, we're almost able to actually model the introduction of electric semis now. We just need a few more assumptions. The first is that companies will only replace trucks that have finished their lifetime. After all, they'd be losing money otherwise. And the second was that the total number of semis has stabilized. This was supported by our data and allows us to make the very useful assumption that the number of trucks purchased in each year is equal to the number that expire in that year. Now for each year, our model does three things. It computes the number of electric semis produced by summing the production function over the 4 quarters of that year. It computes the number of expired trucks using their expected lifetime. So for example, we found that the diesel truck's lifetime was 12 years, which meant that in year N, every single truck produced in year N minus 12 was expiring. And then we took these expired trucks and replaced as many as possible with electric semis, since we've established that electric semis are better. Now our calculations were done inside of this table. So we have a max production column, which is the maximum number of electric semis that the industry could produce in any given year. And when that number isn't enough to meet the number expired, we have to produce some diesel trucks, which you see on the left. Then we have two expired columns, which, as we already discussed, just keep track of the trucks that have reached the end of their lifetime. And finally, we have the sold column. The sold column is the actual number of electric trucks that are being introduced in each year. It's separate from max production because in some cases, max production is greater than the number of trucks that expire. And we know that those extra trucks will not be purchased or produced. Now, in-service just keeps track of these sold trucks. It adds them in and subtracts out the expired trucks. And we just take this in-service number divided by the total number of electric trucks, the total number of trucks, to find the proportion of semis that are electric. Now doing so, we have our results. In 5 years, the percentage of semis that are electric is 34.6%. In 10 years, it's 79.6%. And in 20 years, it's 92.4%. Now that we have our results, we want to see how sensitive our model is. So to do our sensitivity analysis, we rewrite our production function in a more generalized form. So you can see here that we have 3 parameters, and these are the only 3 parameters of our model, and we will just vary them to see how our results turn out. So the first parameter is K here. K is essentially the steady state production of the industry. We can see that when that number increases, the proportion of electric semis will increase as well, which makes sense. And likewise, when it decreases, the proportion decreases. A and R are more of growth factors, and we can't really quantify their effects very easily. However, we can see that when we make these small changes in A and R, the percent changes in our results are likewise small, and that gives us more confidence in the robustness of our model.
So for problem 2, we were given 5 different major freight corridors in the US to and from major cities. And with these corridors, we're tasked with finding the number of charging stations and the number of chargers at each station necessary to supply all of the electric semi-trucks if all trucks were converted. Now, we made 2 main assumptions to accompany our model. There are more, but these are the 2 most important ones. The first is that electric semi-batteries should be charged at 20% up to 80% capacity. This is compliant with research we did on battery charging guidelines to preserve battery life. Semis are also uniformly distributed down the corridor. This simplified a lot of the calculations we had to make, and if traffic volume was consistent along the entire route, it allowed us to evenly space the charging stations in our model. So here's a graphic that illustrates how our model works. We have our charging stations evenly spaced down the route, and we assume the worst case scenario if a truck enters the corridor at the lowest possible charge, which is 20%. At that point, it would need to seek charge at a charging station. We added an arbitrary 10% buffer so that a truck could get to any nearby charging station, no matter where it is along the route, within 10% of its battery. And this 10% battery translates to 40 miles traveled. So that's how we figured out how to space our charging stations, each 40 miles apart. Now with this, we came up with a simple formula based on the total distance of the corridor and this spacing. So this spacing is represented by the maximum distance that can be traveled by a battery on full charge multiplied by 10%. And then we divided the total distance by this value, which is 40 miles, to get the number of stations we would need to partition the corridor. Then we added 2 as stations at the start and end of the corridor. And then we ceiling this value for a more conservative estimate.
To find the number of chargers at each station, we used these 2 equations. We first found the average number of semi-trucks that travel along each route in a day by multiplying the percent of semi-trucks, or Class A trucks on the road compared to all classes of trucks. AADTT values are the average annual daily truck traffic along each route. Then, to find the number of chargers per station, we use the second equation. Peak ratio is a percent of total daily traffic through a point at peak times. Charge time is the amount of time that it takes to charge from 20 to 80%, which is about 4 hours. And on-road was found in the first equation. The number of trucks is then multiplied with the route distance divided by battery max, which gives the number of times a truck needs to recharge along the entire route. The final value is then divided by the number of stations to evenly space the total number of chargers at each station along the route. Our model found that the number of chargers and stations along each route was directly proportional to peak traffic and route distance, respectively. So as the corridor distance increased, then the number of stations would have to increase as well. And if the number of trucks at peak times increased, the number of chargers would have to increase at each station. Our model is an overestimation of needed chargers to account for the worst possible scenario. We decided to overestimate because an underestimate of needed chargers would lead to many battery shortages along each route and cause many trucks to become stranded due to a dead battery. Since AADTT values are averages, they don't account for increased trucking demand during holiday seasons. But in a more comprehensive model, we could approximate the traffic data using the normal model to account for times with a higher traffic volume.
Problem 3 expands on the hypothetical questions presented in problems 1 and 2 by asking us to create a model to determine implementation order of electric semis and testing it on the 5 corridors mentioned in problem 2. To proceed with our model, we have to have 3 essential assumptions. The first is that corridor implementation is primarily driven by environmental, economic, and political factors. The primary focus of a switch to electric vehicles is environmental in nature, with questions about the sustainability of fossil fuels and the potential ramifications of global warming. However, implementation of electric semis is only possible if it is economically and politically sound to do so. If it is not economically sound, companies will be unwilling to invest into the infrastructure required to transition. If it is not politically sound to do so, Politicians will be wary to pass policy to support the implementation of electric semis, which would hinder growth. Thus, we decided to base our model on these factors. The next assumption is that each of the parameters used are weighted equally. By weighing each parameter equally, we minimize subjectivity in the relative importance of parameters, which adds neutrality to our model. And finally, for each of the parameters in our model, we will be calculating z-statistics, which indicate how far above the mean level of support for each parameter. With these z-statistics, we will be summing them together. Although it is simplistic, summing the z-scores provides an easy way to compare the effects of parameters in individual cities, such as when both the public support of electric semis and the costs of infrastructure are high. In this case, the high public support would be conducive to implementation, while the high costs will be not conducive to implementation. Our model primarily focuses on 4 factors: public support, which takes into account political factors; carbon emissions costs, which takes into account environmental factors; and projected development costs and usage, which takes into consideration economic factors.
And so in our final results, we have the table of the final values, which were calculated from the equations from the model parameter side, and below that, the standardized values and the monetary transition index score, which was used to determine which corridors would be the best to develop. And so first, for the public support column, the California corridor has the highest public support because it has the most market share of alternative fuel cell vehicles, while the Texas to Louisiana route has the lowest. And in the carbon emissions category, which is mostly dependent on length, the Texas to Louisiana route has the most to benefit from the transition, while the Minnesota to Illinois route has the least to benefit. In the usage category, the Texas to Louisiana route has the most to gain from it, and the Florida to DC route has the least to gain from the transition because it has the lowest usage. Finally, the projected development cost, which is based on the calculations from our problem 2 solution. We found that the Texas to Louisiana route has the highest development cost because of the amount of charging stations that have to be built, and the Minnesota to Illinois route has the lowest development cost, so it would be the best in that case. And so once we collected all these values, we standardized them by giving them all a z-score, and so this weighted all of the categories equally because we were unsure which category should be weighted more than others, so it's best to keep them all weighted equally. And so the trends all remain the same, leading to our monetary transition index score, which was the summation of all of the z-scores for each corridor. And so this led us to the winner of the index score being the California corridor, because it had the highest index score, so it would be the most favorable to develop, while the Minnesota to Illinois route would be the least favorable to develop. And second, you have the Texas to Louisiana route, followed by the Florida to DC route, and then Massachusetts to Pennsylvania route, and finally you have that Minnesota to Illinois route. One key point to point out here is that all the categories were weighted equally, and different companies might consider different categories to be more important than others, and so that would change their index score if they were decided to weight it differently. We decided to weight them all equally because we were unsure about which companies would want to prioritize which different categories. And the ranking of the corridors shouldn't change significantly because the factors that we use to estimate the various categories were pretty accurate. As long as the weighting of the categories doesn't change, the final ranking given by the index score should not change significantly.